5.1 through 5.4. Okay, just to remind you, 5.1, if you recall, we began 5.1 with the concept of what is work. We were defining work as the product of force times distance times the cosine of theta. And then in 5.2, we started to take that concept of work and apply it to kinetic energy. We learned about types of energy like kinetic energy and potential energy. And then we talked about the work kinetic energy theorem. In 5.3, we looked at overall conservation of energy. MEI equals MEF. And then in 5.4, we looked at power. Okay, so those are our 4 topics we're going to look at today. The easiest way to do this, honestly, is to look at the formulas involved and discuss what you're going to be expected of. So in 5.1, we'll start with 5.1. So we started with work, and work equals force times distance times the cosine of theta. Now, recall, please, that the force in this example is a constant force. It's not a changing force. Again, it's a constant force. It's not, because if the force changed, we'd have to do something called an integral in calculus, where you calculate an area under a curve. And it would work, but it's something that you haven't gotten to yet in your math class. So for now, we're saying that the force is constant. Okay, the force is not changing. The distance traveled is that, exactly, it's the distance, not the displacement. The distance, not the displacement. So if I apply a certain amount of force on an object, 10 newtons, right, for 8 meters, and then I apply 10 newtons for another 2 meters back the other way, I use 8 plus the 2 to give me 10 as my distance. I don't think like, okay, that's 8, and then back 2 makes the displacement only 6 meters. This is distance applied, or distance traveled while the force is applied. Theta is the angle between the force and the motion. The angle between the force and the motion. Okay? Now, how do we relate this to section 5.4? In 5.4, we talked about how power is work over time, or power is the change in energy over time. So as a result here, if you got an answer for work, let's say we have a number here. Let's say that somebody applies a certain force of 10 newtons for a distance of 15 meters at an angle of 20 degrees above the ground. That's what I would plug in. Again, 10 newtons of force. So this is like remember you're pulling your brother or sister in a sled? This is this example, exactly. You're pulling at an angle of 20 degrees. Look at my arm. It's around 20 degrees above the horizontal. The direction of motion is horizontal. The force is my arm. So here's the angle, 20 degrees right there. So I'm pulling at an angle of 20 degrees for 15 meters, or pretty much 15 steps. And that's the amount of force I have to apply to this object to overcome friction. Okay, now, what's applying back against it? Friction is pulling back. So friction is also doing work on this object, but I'm looking at the work done by the person. This is like my applied force. Remember, F is whatever the force is that's doing the work. If friction is doing the work, then F is really FF. If a person is pulling on the object to do work, then F is like FP, we called it, push or pull. So F takes on whatever role you're looking at. If I ask you to find the work done by friction on this object, now I'm saying, find FF. You can replace FF with mu Fn if you want to. You could use your old formulas to help. Now, if you calculate this, what do you get? Somebody do it real quick. Just give me a number, please. So the nearest joule is fine right now. Go ahead.
140.95.
Okay, so 141 is the nearest joule. Say 141 joules. Just trying to go quick. So if we're trying to figure out the power that is generated by the person pulling, we also need to know how much time has elapsed. So let's say that 12 seconds have gone by. If 12 seconds have gone by, how do we figure out the power generated by this person? What is it? Yeah, power equals work over time. So we take this number and we divide it by 12 seconds. That gives me the answer in the amount of power, or as far as the amount of power generated by this person pulling. I'm probably going to give you a problem that has the word watts in it, so you should know what watts mean. Yeah, you probably shouldn't leave it in joules per second. Whenever you can put a simplified unit, you should always put a simplified unit. So you should put watts. It is a joule per second, though, yes. It is a joule per second. So whatever this comes out to be, it really doesn't matter. It's going to be around 12, what? 11.75, all right. Okay, so around 11.8 watts. But the idea that work and power are related is something that you should understand. Because remember that power is the rate at which work is done, or the rate at which energy is transferred. That's what power really is. It happens to be also force times speed, but that's not really the definition of power. The definition of power is really defined as the rate at which work is done, or the rate at which energy is used. Okay? Make sense? Work with that. In 5.2, we introduced the concept of kinetic and potential energy, and then we related that to work. Let's go ahead and look at that now. So this was also a little bit 5.4 for power, obviously, right? Okay, a little touch on 5.4 there. In 5.2, we talked about kinetic energy being a half mv squared, potential energy being mgy, potential energy in a spring being 1/2 kx squared. And then we also talked about this governing theorem, W equals delta Ke, which we talked about at the start of today's class when we were looking at power earlier, right? So work is equal to the change in kinetic energy. This is true when there's no vertical motion. Remember, when there's no vertical motion, this is true. I'm doing it?
No, I did.
So the work, again, done is the change in kinetic energy of the object. So if I push an object and it makes it speed up, I'm doing work on the object. Even if I push an object and it actually stays at a constant rate, I'm still technically doing work on that object. And we'll talk about how that works then. It has to do with the balance of friction force and your applied force. Now, what about these three formulas? What could you tell me? What is kinetic energy based on, pretty much? Kinetic energy needs to have what? What does kinetic energy need to have? Look at the formula. It needs mass and it needs velocity. Now, all objects have mass, so mass is there, right? So pretty much the object needs to be moving to have any kinetic energy. To have potential energy, or I should say gravitational potential energy, meaning this one right here. To have gravitational potential energy, what do I need to have? Mass, again, which all objects have. Gravity, which is on the Earth. What is the last part, Katie?
Height.
Yeah, height above what? Yeah, above whatever you call the ground. So, I talked about this with you several times. This pen right now on the table, right, sitting on the table, has potential energy if I'm considering the floor to be the ground, right? It's about 1 meter above the ground, so it's got some potential energy. But if I'm calling this lab table the ground, and this is sitting on the lab table, it now has 0 potential energy. So it's all relative. Remember that potential energy dashed blue line in the lab just now that you moved to the bottom of the ramp? You defined the bottom of that half pipe to be ground level, even though it's not really ground level, right? Where's ground level really? It's all relative. You don't know. Like, yeah, sure, you want to say Park Avenue's ground level, but concrete's been put on top of what was there already. So what really is ground level? It's a theoretical concept. So, again, if I consider this to be ground level up here, and it falls to here, you'd say it actually has negative potential energy down here. Okay, but the idea is that it's relative. So if you start somewhere here, and it ends up here, you should probably call where it started the ground. If you start up here, and it ends down here, you should probably call down here the ground. So the lowest point of the object's motion you should probably define as ground level. That will make problems a lot easier when you're doing them. Okay, a lot of the mathematical portions, you want to define ground level as the lowest point of the object. You should probably write that down. I'm telling you this, right?
So if I were to take, right, like a pen, and I were to just throw it up, right,
In the air.
I'm sitting here, feet above the ground. I would still put my ground level for the problem would be the lowest point, which would probably be, let's say, after here.
Where's it going to land?
It'd be here. Well,
Where's it going to land?
it doesn't matter. It's going up.
Oh, so then call this ground level, absolutely.
Then this
Just like in the lab that we tried to do with the
So that was
we call it ground level where you release it, right? Same way.
Wait, so ground level is the lowest point in an object?
Of the object in its path. Now again, ready? I might be looking at this example where I'm tossing this marker up in the air. And I want to know from here where it starts, how high is it going to get? I don't care what happens afterward if it falls back down to the ground down there. So I'm going to call the lowest point in the path ground level. So the lowest point in this path is probably right here, where it's released. Okay, so if this object is dropped from up here, and it falls to the table is now ground level. If it falls from up here to down here, the floor is now ground level. Do you see what I'm saying? The lowest point in its path in that situation or in that scenario. Okay? It makes it a lot easier on you because at that point, it has no potential energy. If it can reach that point, right, when it comes from here, jumps off the cliff, lands on the ground, you can call that zero potential energy. So at that point, it's only got kinetic. It makes life so much easier for you. Don't call this the ground, because then you got potential energy here, and you've got potential energy here. That's an extra part to the equation. It just simplifies the work for you by doing this. Now, if I were to increase the velocity of an object, what increases? If I increase the velocity, what increases? Look at the board. What increases if I increase velocity? Kinetic energy. What changes or what happens if I decrease height? If I decrease height?
Potential energy decreases.
Very good. So we understand the direct and indirect relationship concepts again, right? So if I were to tell you this, what if I double the mass and quadruple the velocity? What happens to the kinetic energy? If I were to double the mass and quadruple the velocity. So double the mass and quadruple the velocity. Remember, this is our normal kinetic energy formula right above it. That's our normal kinetic energy formula in yellow. But I'm telling you double the mass and quadruple the velocity, which is what I've done here in white. What effect does that have on the overall kinetic energy?
You're just multiplying
By 8? I would say you're close.
Oh,
There's a little mistake.
By 18?
No.
Oh, then 32.
32. Can you explain?
I heard it. 4 to the power of 2
Is
16
times.
2 times 16 is 32.
Think about how it changes. Ready? I'm going to show you what Theo just said. Ready? You got the 1/2 here. You've got the m. You've got the v squared. Well, what's left over? This 2 is still here, isn't it? So that can go right here. Remember, multiplication is commutative. I can move the order. The v has been squared from here, but I also have to square the 4, which means you're missing a 16. As a result, the kinetic energy that we currently have is really 1/2 mv squared times some factor of 32. So as a result, you could say that the kinetic energy has gone up by a factor of 32. Again, double the mass, quadruple the velocity. These are the factors of increase as a result. The product of these two is indeed 32. If I did it simpler though, and I was just really nice and I said, if I triple the velocity, what happens to the kinetic energy? You should be able to answer within a split second. Goes up by? 9. Very good. If I quintuple, meaning increase the velocity by a factor of 5, what happens to the kinetic energy? What does it go up by?
25.
By a factor of 25. Where am I getting these answers? Where are they getting these answers? What are you guys doing?
Square.
You're squaring it. If you put a number in front of v, don't you have to square it? It's in the parentheses. So if I increase the velocity by 8-fold, the kinetic energy goes up by 64. Because 8 squared will give you a factor of 64. This is all under the assumption that I'm not also changing the mass, right? I just gave you another scenario now, and those scenarios involved a mass that wasn't changing. The one that we just did, though, on the board that you see here involved where we doubled the mass and quadrupled the velocity. You could do more than one thing at a time. Yes?
Wait, so can you give another example of just like changes, like when you use the word, just say like if I.
So if I were to double the velocity,
Yeah.
what happens is this.
I know it becomes 4.
Yeah, the 2 becomes a.
Yeah.
So all you have to answer is it goes up by a factor of 4.
Oh, so like
I triple the
When
velocity.
you use the words, it's 2 words actually.
So there's double, triple, quadruple. Those are really the ones you should know.
Okay.
You don't have to know quintuple or septuple or any of those.
Yeah, that was it.
Yeah, so pretty much double, triple, quadruple. Those ones are the ones that you should know. I might just say, if I increase the velocity, or if you increase the velocity by a factor of 7, that means put a 7 here, which makes it 49. Okay? How about this one? An object falls halfway from its initial height to the earth. What can you say? What can you conclude about its energies? An object falls, so here's the height it's at. The ground level is the floor. It falls halfway. At the halfway point, at that instant in time, what can you tell me about its energies?
Oh.
It's kinetic energy and potential energy are equal.
Absolutely right. That makes sense?
Yeah.
Why? Who can explain it besides Benham? Who can explain why that is true? Katie.
Because there's motion as well as height.
Good. Motion as well as height, so it has both. Good. But how do you know that they're equal? How do you know that they're both equal?
Because it's halfway.
Yeah. If it's halfway, it means it's lost half of its potential energy. Where'd it go? We're assuming no friction, right? Where'd it go? Kinetic energy. The half of potential energy it lost as it fell halfway to the earth went into kinetic energy. So at this instant, it's got both. Beyond this instant, it has more what energy? More kinetic down here. Above the halfway point, it has more potential. Does that make sense? This is talking about the free fall. This is the skateboarder in the skate park, just as you did. At the bottom, it was all kinetic. At the top, it was all potential. In between, it was a little bit of each. If an object falls from the sky, from up here, where it's at a certain height, and I tell you along the way it loses 7 joules of energy to friction, and you want to still calculate the velocity at the end, how do you approach a problem like that? Starts on a cliff somewhere, falls to the earth, like so. Your goal is to figure out what is the velocity at the end. Imagine you're given the mass, you're given the height, you're given all the other information you need. Okay, everything's given. But I tell you that on the way down, it loses 7 joules of energy to friction. How do you approach this problem? We haven't done something like this yet. I feel like we've talked about it, and we've talked about where it goes in the equation, right? So how does this, the question is really like, how does this equation change if there's friction involved? What do we have to do to this equation? We did it in our notes. If you look at your notes in 5.3, we talked about it. And?
Maybe first you find potential energy at the start, then you find kinetic energy at the bottom, but you take away 7 from that kinetic energy final.
Close. It's the other way around. You don't take away 7.
Oh, you add, wait, why would you add 7?
Because isn't the kinetic energy going to be 7 joules less than what the potential started at? It loses energy, right?
Yeah, it should be less, right?
So you need to have 7 more to make a balance. Think about balancing the equation.
Oh,
Right?
okay.
Think about it this way, guys. If you started with 20 joules of potential and you lost 7 on the way, what does that leave for kinetic?
Oh, you added it because it has to be.
Yeah, you have 20 joules of potential to start and you lose 7 along the way. How many are left to kinetic? Answer the question.
14. Wait, what?
Start with
Oh,
20.
13. Am I stupid?
20 potential.
It's
You lose 7 along the way.
13.
Therefore, kinetic is 13. Isn't 13 plus 7 back to 20?
Yeah.
So whenever you lose energy, that's Q loss. That's why, if you recall, I had you guys write this down, or I think I actually wrote it in your notes that you have it typed up already for you. I put plus Q loss over here at the end. And I put absolute value, so no matter what you have a sign for now, you know that you're adding on some quantity of energy that's lost. And think about it logically, please. You start with more energy than you end with if you lose energy. So where do you have to put it to balance? You have to put it at the end. You got to put it at the end to balance because you're losing this energy along the way. So final is going to be less than initial. So to make the final a little bit more, you add some number to it.
So basically, you never really lose the.
No, the energy is always there. It just goes to thermal. That's the whole idea of conservation. Energy cannot be created nor destroyed. But it can be transferred or changed or morphed or whatever word you want to use.
So,
I'm listening.
can't it be lost in thermal? Can't energy be lost?
Yeah, we could use the word lost, or we could just say transferred to thermal energy.
But then what's the loss from, it's not friction. but
Friction, thermal, they're all the same thing.
But what's the, is there any change in amount of energy from kinetic to friction, even if it's like a really small number?
Saying there's no vertical motion you're talking about?
Yeah.
So if an object's doing this?
Like if I'm rubbing my hands together and I'm creating thermal energy, is it an exact, is
absolutely.
there no loss?
Absolutely no loss. So the exact amount of energy you are giving it in kinetic energy goes all into thermal. Yep, all that energy that's coming out of this is all thermal energy that's on your hand side. Now obviously, as you move up and down, you're changing potential, but because you're doing it in a cyclical manner, the net change of potential is 0. Right? Okay, but the idea is here, kinetic energy creates thermal energy. Yeah?
So if the initial energy was 20, then the kinetic, final kinetic energy would be 13?
Yeah. So you have to figure out the velocity, right? So I want you to find the velocity. So I'll give you the height, I'll give you the mass of everything. So for here, PE goes in mgy. Right? So potential energy is mgy. Let's say we don't know the energies. Kinetic is 1/2 mv squared plus the 7 lost of friction on the way down.
So that would be 20 joules, right?
Yeah, but I gave a number of 20. Let's make believe I don't have the number. Let me make believe I told you that the mass of the object was 7 kilograms. The height of the object on the cliff was 20 meters. And your goal is to figure out what the velocity is. Oops, that's a squared symbol. Okay, so all you have to do is plug in 7 is the mass, times 9.81, times 20, which is the height you started at, equals 1/2 times 7, which is the mass, times v squared, plus the 7 joules of energy lost to friction. So you'd have to solve for v in that problem. You could solve generically also. You could always solve generically. Instead of putting a 7 here for Q loss, you could write Q loss. Subtract Q loss, multiply by 2, divide by m, take the square root. So these problems are not, you don't have to plug in numbers if you don't want to.
Is the object 7?
I know, I used 7 twice, sorry. Let's say Q loss was like 12 joules instead, so it's not confusing anybody. Okay? Okay, say it lost 12 joules, that's fine. But yeah, the object's mass is 7 kilograms. So this is what I was trying to really highlight in the other class we reviewed yesterday. The concepts here have to be able to be applied. If you can't apply them, you're not going to do well in the math portion. You have to be able to apply them. So let's look at another scenario now. And all I'm going to ask you to do is come up with what kind of energy does it have at what different state. In the beginning, what energy does it have? At the end, what energy does it have? How do we relate those two? Is there friction involved? Okay, that's the hardest part for these problems. Once you honestly plug in the formula, from this line down should be easy work for you. You should be able to solve for V. That's not hard. It's basic algebra. You should be able to do that by now. If you want to practice that with me after school, I'm happy to help you with this stuff. I don't mean that like it's not something you can't not be necessarily pro at, but you should be able to do this. The harder part of these problems does come in the beginning. Okay? So let's look at an example. Let's say an object starts, let's say an object starts on the ground. Okay? An object starts on the ground and it's compressing a spring.
Is it still 5 through 2?
This is still like 5.3, yeah.
Okay.
I'm not going to do too much with 5.4 because we literally just did that. Power and stuff we just talked about yesterday and today. So I'm not going to go into crazy review for that. This is still 5.2, 5.3 are kind of the same thing. 5.2 we introduced kinetic potential and potential spring and the work kinetic energy theorem. And then in 5.3 we looked at conservation, which applied all those formulas anyway.
We just did 5.4.
Yeah, 5.4 we just did yesterday and we did that also this morning. So we're not going to go into too much detail on 5.4. So here's a cliff. We'll say that the object on the ground is compressing a spring. We know that the height of the cliff in this problem is, how tall? 10? What? 10 meters? Okay. And our goal is to figure out how far the spring needs to be compressed. How far does the spring need to be compressed? We're told that when the object lands on the cliff, it has a velocity of 2 meters per second. when it lands on the cliff. We're also told that the mass of the object is 1 kilogram, and that the spring constant of the spring, it's a very strong spring, is 1,000 newtons per meter. You need to know your units. That's another thing. If you see newtons per meter, right away, spring constant. It's the only thing that's a newton per meter. Nothing else we've done all year has units of newtons per meter. K is the only thing we've done so far. So when you see newtons per meter next to a number, even if you don't know what spring constant means, you should know that newtons per meter is your K value. Okay? The mass is 1 kilogram. We want to figure out what should the spring be compressed by, or how far should the spring be compressed. What are we looking for then? What variable is that in your spring formula?
Is it X?
It is X. Very good. Remember, X is the final spring position minus the initial spring position, or the natural spring length subtracted by the actual spring length is how much it's been compressed by. So if a spring is like, there are springs, by the way, you're used to like little springs, right?
Yeah.
But there are springs at the end of a train track line that are like meters long. Why are they there? At the end of a train line, why are there huge springs?
Well, the train stops, that's something to push against.
Yeah, if the train cannot stop using its own brakes, that's its only safety mechanism, by the way. They don't actually use it normally. But if it doesn't stop on its own, you don't want the train running into the station, right? So there's a spring there. The spring will literally absorb the energy and kind of push it back. Okay? It's a giant spring. So imagine this is a very long spring, or a strong spring, we could say. And we're trying to figure out by how much does it compress. That's X. But if I know it's 6 meters long, and once it's compressed, it's now 4 meters long, well, how much has it compressed? It was 6, it's now 4. How much did it compress by? 2 meters. So really, X, which is what we're solving for in this problem, is the free length minus the actual length, giving you the compression length. We went over this in your notes. It's already in your notes, all this. You could write it down, though. Again, X is the compression length. That's the free length of the spring minus the actual length once it's been compressed, giving you how much it's been compressed by. So if we're trying to find X, we need to set up our conservation of energy formula, which tells me MEI equals MEF. Let's also say that on the way up, how much energy was lost? A half a joule to air resistance. Okay, I'm not going to give you, I'm always going to give you the number of Q loss in joules. I'm not going to say like force of friction was applied to the object and this, and you have to figure out what Q loss is. That's a lot. You can do it. It's not impossible. We did do it in one of our examples, but it's a lot more time there. So I'm going to say it lost a half a joule on the way up. So I need my conservation of energy now. This is it's not an easy problem what we're doing right now. This would definitely be like toward the end of your test, difficulty-wise. So I start with MEI equals MEF, right? My governing formula. MEI equals MEF. Now, I have some sort of loss in energy. Where's that going to go again? Yeah, on the right-hand side, MEF. That's a Q. Okay, some energy lost. So at the end, it's going to have less energy, so you have to put the Q loss on the end to balance out what it had to start.
Will you always include Q loss?
Not in every problem. Some problems I'll say, in this problem, it's a frictionless problem, or I just won't even talk about losing energy to friction, and then you assume it's frictionless. Unless you're given something that says it loses energy, which is Q loss, you don't have Q loss.
Because in the textbook, there's not a lot of Q loss.
No, there's not, because it makes things a little more complicated than like the basic problem. So in this problem, what kind of energy does it have to start?
What was that?
What? I know, that's too fast. What kind of energy does it have to start? To start. Elastic. Why? Potential elastic, or potential spring, we call it. Why?
Because it's compressing the spring.
It's only compressing the spring. Now, granted, that spring is kind of above ground, but what are we going to do? We're going to call ground level where the object starts. Remember, the ground level is always the lowest point of the object's path. So see that dashed line right there? That's ground level. Why do I do that? Why do I make ground level there and not the actual ground?
Because the spring can be compressed any further than that.
Yeah, but what does it do to my math? I'm saying, like, you're right, absolutely, Klaus. But why am I calling this ground level and not calling this down here ground level?
You have to solve for the empty space.
After what?
You have to like solve for the empty space of the difference.
Yeah, you'd have to also account for that empty space, but you'd have to account for the energy if it wasn't there. So, like, let's say this is 2 meters right here. What's the actual potential energy at the end going to be? Its height at the end with respect to ground level. 8 meters. So you need to be able to figure out that that spring goes from some location to another. If you call the bottom ground level, then it starts with potential energy. It ends with potential energy. It's ruling out the potential energy in the beginning. It makes life easier. So let's take this equation right here and go a little bit further. Okay, let's go a little bit further with this equation. So MEI is the energy in the beginning. So you have potential energy in the spring. You don't have any potential energy because it's at ground level. You don't have any kinetic energy because initially it's not moving. So those both drop off. Remember, you don't have to write these. I'm doing it to show you. Okay? If you recognize the kind of energy the system has in the beginning and you want to just list that energy, you could start with PES equals. That's fine. On the end of the problem, it reaches that height of 10 meters above the Earth, but 8 meters above where it started. Does everybody see that? Look where it started, look where it ended. It's moved 8 meters vertically. I don't care about the path it took. I don't care that it got all the way up to that height at the top and then came back down, right? It reached that apex and then came back down further. Just look at the final position relative to the initial position. The final position is right here. One sec, Honor. Is right here. The initial position was right here. That's a vertical change of 8 meters. So it has some potential energy at the end. It does not have a spring at the end, right? There's no spring at the end. So it has potential energy at the end. It's also moving. The instant before it lands on the cliff, it's got a velocity of 2 meters per second. So it has kinetic energy at the end. And we've lost energy to Q loss along the way. So this formula simplified is really just this then. I'm going to write it on this line right here. Okay, that's the formula really at the bottom. And if you can analyze the problem and jump right to this formula, you should. You should say, well, in the beginning there was only a spring. There was no actual initial velocity because it was at rest in the spring. The spring is what gave it the velocity. There was no height to start, so those are gone. At the end of the problem, it didn't land on a spring to compress, so that's gone. But it did have some height at the end of the problem. It did have velocity at the end of the problem, and it did lose energy along the way. So that's where this formula comes from. Hunter.
So like on a test, one question was, you said 8 meters. Does that mean that you would tell us like what the space is between?
Absolutely, you'd have to be given that. Or I might tell you, God bless you. Or I might tell you a spring is launched and ends on a cliff 8 meters above the ground. If you're not given any information about this gap here, then you assume the spring is compressed all the way to the ground. Yeah, if you were given this information of 2 meters, you have to account for it. But if it says an object is at ground level in a spring that's compressed, you assume that the spring has been compressed all the way to the ground. Or maybe the spring is actually in the ground and the object has come down to the ground. Okay? So if we were to go ahead and plug in our variables, we know we have a lot of variables here involved. For energy in a spring, it's 1/2 kx squared. That's all the energy. That's it. In the very beginning, all you have is a spring. When it hits the cliff at the top, it's got potential energy. It's got kinetic energy. And some energy has been lost along the way. Again, all I'm doing is using my formula sheet. 1/2 kx squared goes in for PES. MGY goes in for PE. 1/2 mv squared goes in for KE. I'm applying subscripts accordingly. F for final. So our goal was to figure out how far the spring had been compressed. So what are we looking for again?
The kx.
Yeah, specifically though, not the kx squared. What do you? Yeah, just x. You're given k. So if I were doing this and I were taking the test, I might plug in numbers at this point and solve for x because I know everything else. Or I might solve for x generically. Focus, guys, focus, I know. I might solve for x generically. Okay, so either way works. You know k's value, you can plug it in. You know the mass, you know yf, that's 8. You know the mass, you know the velocity, you know your gravity's on Earth. Q loss is 0.5 joules. You could plug in everything and just solve for x at this point. In all of these problems, if you want to plug in early and solve, I don't mind, it's fine.
What else would we do?
Solve generically. You would have to multiply by 2, then divide by k, and then take the square root. Remember how you solve for x by itself? Isolate the variable. Or just plug in all the numbers and then solve. Okay? Office hours after school, please don't forget if you want to come by.